Hey Matrix, welcome to the last video in the physics playlist. Today I'm covering question 10 of the November 2020 past paper. If you don't have the past paper, there's a link in the description below where you can download the paper as well as the memo, and then we can continue with the video. Okay, let's get started with question 10. Okay, so question 10 is looking at an experiment where we're looking at the relationship between the frequency of light incident on a metal and the maximum kinetic energy of the emitted electron from the surface of the metal. Okay, then they give you the table or graph down here. We've got potassium, zinc, and platinum. Okay, we can see that we're dealing with frequency on our x-axis and maximum kinetic energy on our y-axis. Okay, so the first thing that you should realize when we're dealing with this is this kind of question is always going to deal with the photoelectric effect. Okay, now just a quick overview of what the photoelectric effect is. Okay, so you have this incident light that's coming in onto the surface of your metal. But now remember, your metal is made up, the atom arrangements inside the metal has a sea of electrons. So what happens is this incident light ray hits one of the electrons and now it energizes the electron. Okay, so it ejects the electron, okay, from the metal, but now we have one less electron in here. So what happens is we have an electron from further down in the sea of electrons, it moves up, okay, to fill this electron gap over here. This is why it always gets extracted from the surface of the metal. Okay, so the ones right at the surface, the electron here, let's say we have an incident light coming in, it kicks it out, and we have an electron from further down moving up. Okay, and then if you put a potential, so a negative positive here and a negative here, the electrons are attracted to the negative, and you can then create a circuit with a light bulb, and that's pretty much how solar panels work. Okay, so for this question 10.1, it's asking name the phenomenon for which the experiment is based on. Okay, that's your photoelectric effect. Okay, so we can produce power by ejecting electrons from the surface of a metal. Okay, now 10.2 says the type of physical quantity represented by x on the graph. Okay, so note that x is down here on the bottom of my y-axis. It's a negative x that's being represented there, but we know that the maximum kinetic energy is being represented on my y-axis. So if I had to take the difference between 0 and negative x, okay, I'm taking the change in kinetic energy. Okay, and if I'm taking the change in kinetic energy, then I'm dealing with my work function. Okay, so because your y-axis is measured in energy, okay, if I take the change in energy, which is equivalent to the change in y, we're dealing with the work function. Why? Because work is equal to the change in energy. Okay, now 10.3, it's worded a little bit funny, but 10.3 says which one of the three metals needs incident light with the largest wavelength for the emission of electrons. So what it's asking is, out of these three metals, which one's going to need the largest wavelength in order to eject the electron from the surface of the metal? Okay, now you should recall that wavelength, so lambda, is inversely proportional to my frequency. All your frequency is inversely proportional to lambda. Okay, so what does that mean? If frequency increases, okay, my wavelength is decreasing. But if my frequency then decreases, my wavelength must increase. So if we just look at the graph here, which one is the smallest frequency? Well, we can see over here, potassium does. So because potassium has the smallest frequency, okay, I'm decreasing my frequency over here, which means I'm increasing lambda, therefore increasing my wavelength. So the one that needs the largest wavelength is then potassium. Okay, now 10.4 says define the term work function in words. Okay, you can go and look at your list of definitions for exactly what's happening in that definition, but the short and sweet of it is the minimum energy required to eject the electron from the surface of the metal. Okay, but go and look up that for the word-for-word definition. Then 10.5, we start with some calculations over here. So 10.5.1 says the work function, calculate the work function for platinum. Okay, so platinum is the last line over here, so we can see it's got the highest frequency. We can also see that our ticks on our x-axis are counting in 0.25, so we know that it's cutting over here at 1.75. Okay, and it's times 10 to the 15. So we need to calculate the work function, so we know that for 10.5.1, okay, the work function is going to equal to Planck's constant times the threshold frequency for the electron in the metal. Okay, so therefore Planck's constant we know is going to be 6.63 times 10 to the negative 34. Okay, then we know that the threshold frequency, which you can get from the graph for platinum, is 1.75 times 10 to the 15. So we can substitute that in. So that's then 1.75 times 10 to the 15. Okay, if you plug that into your calculator, you should get a value of 1.160 times 10 to the negative 18 joules. Okay, so you can see we don't need much energy, okay, in order to eject the electron. Okay, well, not much work needs to be done because we're on the magnitude of negative 18. Okay. Now, if we look at 10.5.2, it says the frequency of the incident light that will emit an electron from the surface of the platinum with a maximum velocity of 5.6 times 10 to the 5 meters. Okay, so because they've given us velocity, okay, this is 10.5.2, they've given us velocity that is 5.60 times 10 to the 5. Okay, we're dealing with work, we need the frequency, so that you should be thinking of kinetic energy. EK equals a half mv squared. Okay, and this will be our max. Okay, and we know that energy is equal to the minimum energy needed to eject the electron, so that's your work function. Okay, but now we need to add more energy to get it up to this speed over here. Okay, so therefore we have to add in more kinetic energy to get the electron up to that speed, and this is where we get the EK from. Okay, now if I substitute everything in, we know that energy is equal to work, so that's just HF. Then my work function is HF0. Okay, and then we have a half mv max squared. Okay, now we need the frequency for the function. That's just Planck's constant. This is my work function, which we've calculated up here already. This is the mass of an electron. Okay, so that's 9.01 times 10 to the negative 34 kilograms. Okay, Planck's constant we know already, we have the maximum velocity, so therefore we can work out our frequency. Okay, so if we substitute in all our values, 9.11, sorry. Okay, so if we substitute everything in, frequency is just going to be Planck's constant over here. That's 6.63 times 10 to the negative 34. Okay, 1.75 times 10 to the 15. Okay, then plus half mass of an electron, 9.11 times 10 to the negative 31. Sorry, got all my units messed up. Okay, and then this needs to be multiplied by my velocity, so 5.60 times 10 to the 5. Okay, and that's squared, and then this whole thing is going to be divided by Planck's constant, which is 6.63 times 10 to the negative 34. Okay, and if you plug that into your calculator, you should get a frequency which is equal to 1.97 times 10 to the 15 hertz. Okay, and that's how we go about doing this question. Okay, if you found today's video helpful, then please leave a thumbs up on the video. It does help me a lot. Please consider subscribing to the channel. There are chemistry videos and maths videos as well. If you have any questions regarding question 10, leave them in the comment section down below and I'll get back to them as soon as I can. And remember, it's never too late to have an OIC moment.